So here's a picture of the actual link. First of all, there's a transmitter that buffers the signal and sends it outside of the IC. And we use oscilloscopes for testing the output quality of that transmitter. Then there's the channel. There's a nice channel up here. We talked about that. That's the passive interconnect between the ICs. Consists of circuit board traces, connectors, backplanes, can be cable, but what Russ likes to call that is a low-pass filter. So it has a frequency-dependent loss. Often these channels are differential, and they have characteristics. They have an impedance, they have reflections, they have crosstalk, things like that tend to impair the signal that's going through the channel, making it a harder job on the receiver. And so since the transmitter has its own kind of characteristics, the channel has its characteristics, those and like crosstalk and things like that, those add up to create the conditions where you have to test the receiver that emulates those. So the receiver detects, retimes, and cleans up the signal, or makes an attempt at that. And so we have to do input testing to determine the receiver's ability to recover this signal. And you saw some eye diagrams before, kind of the far end of the channel, where the eye was really closed, shrunk down. It's pretty hard for a receiver to pull that signal out and make accurate bit decisions. Was that a 1 or a 0, or if it's PAM signaling, was it a 0, a 1, or a 2, or a 3 coming in? So the receiver has to attempt to recover the signal at the end of the channel. What else is inside a receiver? Well, one of the key things we have to test is clock recovery. Clock recovery is an important characteristic, and I did a quick calculation. The fastest digital signals that I've been dealing with recently have been 56 gigabaud signals, and that's about 18 picoseconds. So the receiver has a total of 18 picoseconds to make a decision, what symbol level was that on my input. And most often, most communication channels use an embedded clock, so you have to have a circuit in there to recover the clock. So the clock is embedded in the serial data coming in. You have to recover that clock to strobe your decision circuit to make that decision at the optimum time, within the received signal. So the optimum time to make that, so you give your receiver the best chance of saying, what symbol level was that. We do signal conditioning. Pretty much everybody so far has talked a bit about this. So on the transmitter, it's often called de-emphasis. And that is pre-distortion, where we increase the relative amplitude of transition bits. So the bits where you have a transition would be larger in amplitude than the bits that you don't have transitions. And what that tends to do is give you kind of a gain versus frequency that can offset the loss versus frequency of your channel. And on the receiver, we have a couple different ways of equalizing the signal, and almost every communication channel these days uses both transmit equalization or de-emphasis, so pre-distortion of the transmitted signal, and receive equalization, which is generally in two categories. One is kind of a linear CTLE, continuous time linear equalizer, that counteracts frequency-dependent loss. So again, it kind of emphasizes the high frequencies versus the low frequencies. It does have the unfortunate characteristic of boosting noise. And then there's decision feedback equalization. So it's kind of self-optimizing, where it, depending on the state of the bits before the bit that it's making a decision on, it will adjust its slicing threshold. A few more details on how the receiver equalization is configured. First of all, there's an input buffer, and then the first thing that happens before the decision feedback equalizer is the CTLE, so the kind of the high pass characteristic that opens the eye somewhat. Then we recover a clock off of that somewhat opened eye, and then the DFE kicks in to optimize the signal further before the decision circuit takes place, or the decision takes place in the decision circuitry. There's a couple other things that go into optimizing these channels, and so for high throughput as well as signal integrity. There's data coding and higher order modulation. So we do a thing called scrambling. So you can envision a data stream. If it were truly kind of random, you could have over time really long lengths of non-transition bits. So let's say an example is PRBS. Does everybody know what PRBS is? We talked a bit about it, pseudo-random bit sequences. So PRBS 7, Russ was talking about that. That has a longest run length of 7. So it has 7 ones. That's the longest non-transition length in PRBS 7. PRBS 31 has 31 ones. That's the longest non-transition length, PRBS 31. But if you had real data, TV pictures or something, and you didn't bother to encode them, you could have virtually infinitely long non-transition, like a whole bunch of ones in a row, or zeros in a row, or twos or threes if you're on PAM signaling. But we do coding to ensure that that doesn't happen. So they scramble the signal so that it has a minimum number of transitions. And that keeps your clock recovery happy because, if you don't have any transitions, you got there's no way to recover a clock off of the data stream. So they do coding to scramble the signal so that you don't have these really, really long run lengths of non-transition bits. Higher order modulation. We talked a little bit about this, and Russ had a few eye diagrams in there of PAM4, where you transmit 2 bits per symbol. And this is getting really popular in the high-speed signaling because, companies want to get higher throughput through existing channels. So the baud rate, which is, relative to the frequency response of a channel, the baud rate is half the bit rate for PAM4 signaling. So you can get these signals through, with more complicated transmit and receive circuitry, you could get these signals through the same backplane without, jacking up your rack and your data center and putting in new backplanes. But makes things complicated. You have, higher bandwidth, but you've reduced signal to noise, so you've made both your transmitter and your receiver design more complex. And one of the things that's now getting popular in really high-speed communications is forward error correction. So in the past, a lot of these high-speed channels ran error-free. So you'd hear these numbers like, you can test to 1 e to the minus 12th, or 1 error in a trillion bits. Well, the very, very high-speed channels are so impaired that they don't run error-free, even under ideal conditions. So what they do at that point is they employ something called forward error correction. So they add some overhead bits that help the receive circuitry correct errors that occur in the transmission of the data. So signal conditioning, data coding, higher order modulation, they add more impairment types to that need to be quantified. So we're going to talk a bit more about the types of impairments you add to these signals to test a receiver.